All right, so I hope everybody had a good weekend. Let's see if I can. Okay, so we finished up our first week of quizzes and homework, so we're on to the second one now. And so that's going on. We've got SI this week, tutoring, all these things are continuing like they have. We're going to hopefully finish up our chapter on chemical kinetics today. We've gone through a number of different concepts from rate laws, remember, which is basically the change in some concentration over the change in time. Or no, those aren't rate laws, those are rates, right? We looked at rates, looked at instantaneous versus average rates. We then went on and looked at rate laws, which are the rate equals some rate constant times a concentration, which may or may not be raised to some order. We kind of combined these and did a little black box calculus and came up with what are called the integrated rate laws. And what these do is give us a relationship between the concentration versus time. Okay, remember when we look at rate laws, this all has to do with the initial rate. Okay, and remember those rate laws we can figure out by using a series of reactions where we change the concentration of one reactant while holding the other one constant. Okay? We used a integrated rate law, and we looked at half-lives of first-order reactions. We did some calculations on that, and we finished up last time by looking at what's called a collision model for reactions or kinetics, which says, one, that reactants must run into each other in order to react. Two, they have to run into each other with enough energy in order to react. And number three, they have to sometimes react with a certain orientation. Okay, so we looked at some examples of that. And so this all came from a discussion of really, well, we showed the graph that that the rate constant increases as we increase the temperature. So we're going to look more at that next. So we're going to look at rate constants versus temperature. Then we're going to go on and talk about reaction mechanisms and finish up with a little bit about catalysis. All right? Any questions? All right, so I've got a little clicker question for today. All right. So we looked at this before, and this was just a relationship between the rate constant and the temperature, right? And this just matched what we knew intuitively, right? That as we raise the temperature, a reaction goes faster, right? It's just like cooking in your oven, right? You cook something at a higher temperature, it goes faster. All right. So, is there, well, let's think first. If we're plotting temperature versus rate constant, you know, how would we get that data, right? Or what are some ways that we can actually, if we don't even know it, how can we calculate what the rate constant is? Figure it out experimentally. Anybody remember one way? Yeah.
Can we do the change in K on the top divided by the change in time? Just kind of the delta of both of them?
Well, the change in K over the change in time would give us some kind of slope at some point on this, right? So my question was, if we're going to come up with the data for this table, so we need a K value at each different temperature, right? So how do we get at what what the K value would be. Right? So we've actually looked at two different ways to calculate out what K is. One is to do the experiments for the rate law. Right? So do a series of reactions, right, to determine the rate law, right? And that's those experiments that we did where we would hold one concentration constant, vary the other one, right? And so we get a rate law, and then the next thing we did when we worked through those calculations was just to take that new rate law and plug in some concentration values and the rate value and calculate what K was. Okay, so we did that before. We'd have to do those series of reactions at each of these different temperatures. Okay, so we could get at K that way. The other way is if we could figure out whether this is, well, we could just determine, let's say, concentration versus time, right? And then use either of those integrated rate laws. If it's a first order or a second order, remember we can calculate out what K is from those equations. Okay, so there's two ways we can get at this. But what we want to figure out here is basically, is there a mathematical or an equation relationship between K and T, right? So we haven't seen that yet, all right? And so it turns out, a chemist, I don't remember the year or anything, Arrhenius, made those observations that we already talked about for this collision model, that the fraction of the molecules, or that the rates depends upon the fraction of the molecules with enough energy to react, how many times they collide, and whether they are colliding in the right order. And he was able to deduce this equation right down here. It's called the Arrhenius equation. And so what we notice, well, if we look at what these things are, so we have the rate constant is a small k. E sub a, we talked about that before, is the activation energy. Remember, that's the height of that peak when we look at if we have that reaction coordinate diagram, right, and we have a hump like this, the height of this peak of energy that a molecule has to go over to react was E sub a. Okay, so the activation energy, the gas constant, universal gas constant comes into that. We use this value here. I thought I corrected that. 8.314 joules per degree Kelvin per mole. T is the temperature in Kelvin. And A is something that's called the frequency factor. So that is some constant for a reaction that tells us how easily the reaction takes place when they bump together. Okay, so if that A was big, well, we can just look at the relationship. If A gets bigger, then K is going to get bigger, right? So if they react very easily, if they don't have very many constraints on orientation or anything, then that's going to increase the K. So we won't worry about calculating for that, though. Well, we'll see how we could do it in a minute. So what this equation essentially does is gives us a relationship between the rate constant and two different things that we want to look at. One is the activation energy, all right? So if we think about this, it's e to the minus E sub a, right? So if that activation energy gets bigger, what happens to K? If E sub A gets bigger, does K get bigger or does it get smaller? Gets smaller, right? Because it's a negative exponent. Okay, so as E sub A increases, K gets smaller. Is that what we would expect? Yeah, because the bigger this peak is here, the harder it is for the reaction to take place. So the taller this, or the bigger this E sub A, the smaller the K, so the slower the reaction. All right? The other thing that we can see in here is the temperature. All right, so what happens here if the temperature increases? K is going to increase, right? Because that's going to make this negative exponent smaller. We get a smaller negative exponent as T increases. So as T increases, K is going to get bigger. All right, that's just what we expected as well. All right? So all of these things fit. All right, so like we've seen before, what we'd like to be able to do to be able to figure these things out is be able to somehow plot this so we can get a straight line, right, instead of that big curved line. All right, so we can this Arrhenius equation from giving us this one here on the left, okay, to this form over here. And essentially what it is just a bunch of algebra. All right, so we could look at a couple of these things. If we want to bring this exponent off the exponent and bring it down, what would we have to do? If we have e sub x, how do we solve for this x? We have to take the log of it, right? So if we take the natural log of both sides, we get the natural log of k, and this equals the natural log of a. And then, because we have the natural log of e to that, we'll have a minus. That brings us down e sub a over rt. Or plus, I think. Right? No, minus. It would be plus that value, but it's a minus e sub a. Okay, so we get this. And so that's just from taking the natural log. So then if we rearrange this, we get this equation on the right. So really all they've done is they took this negative part and put it up in front, and they separated out the 1 over t. Okay, the rest of it's all just like I have on the left side. And so this, in fact, is, again, can be looked at as an equation for a line. All right, so we have y equals mx plus b, right? So we plot x is 1 over t versus the natural log of k. So here's the natural log of k versus 1 over t, and we get a straight line. Okay? So what would the slope of this equal? So it would be minus e sub a over r. Okay, so if we plot it out like this, we could calculate this. We notice that it's a negative slope, so e sub a is going to be positive, right, when we change it, and then we just divide it by r. Okay, so another way to do this is to, if we know k values at 2 different temperatures, so say T1 and T2, and we can calculate the E sub a for that. So basically it's like taking the slope of that line But they give us a new equation for this, and essentially all they're doing is taking, if we label these as equations 1 and 2, so they're both the same, they just have values at temperature 1 and values at temperature 2, right? So the K will be different. And so then they just take equation 1 minus equation 2 and do some rearranging, and they come up with this equation over here. All right, so we could say we have natural log of, I have this K1 minus natural log of K2 equals, and it would be this whole thing here, let's see, minus E sub A over RT1 plus natural log of A, and you'd subtract that from the whole other thing, E sub A, this would be E sub A, I don't know if this is really worthwhile going through this, T2 plus natural log of A. All right, so if you manipulate those with some algebra, you end up with this equation up here. Okay, and so what this really does is, like it says up there, if we know K1, if we measured the rate constants at 2 different temperatures, right, then we can calculate the activation energy. Okay? Exciting, huh? Just what you always wanted to do. Okay, so I don't have any examples of this. There is, I think, 1 or 2 examples in the homework. Okay, likely this kind of a calculation is kind of elaborate, takes a while to do. So to give you a tip, it's probably less likely that I would make you do this whole thing on the exam. Okay? Just because. All right, so let's just see what we've done to now. I kind of did all this already. Here's the collision theory, right? We looked at this relationship between K and T, just the curve, basically. And then this Arrhenius equation allows us to do that mathematically and to calculate E sub A. All right? Okay. So that's kind of the last part in this chapter of doing a bunch of mathematical stuff, all right? So we're going to look a little bit more now about what actually takes place in a chemical reaction. And what this is going to get at is the reason why when we determine, or when we want to figure out a rate law, why it must be determined experimentally, all right? If we have a rate law, why can we not just take it from the reaction? So for example, if we look at this reaction down here at the bottom, right, this is bromopropane, you don't need to know that, bromopropane plus water goes to propanol, it's an alcohol, plus HBr, all right? So why can we not just write out the rate law directly from this equation, right? Why does the rate not equal K times C3H7Br times water, all right? In fact, it's not. So here's the actual rate law. Why don't these match? All right? So clearly, well, the reason is, I don't know if it's clearly, but because there's more going on than what we can just see from this balanced equation. Okay? The balanced equation, just all it does is does the bookkeeping. It doesn't tell us what individual steps might take place for this reaction to occur. For example, in this reaction, here's the balanced equation, but it actually takes 3 different steps to accomplish going from these reactants to these products. Okay, so the first step here goes from the bromopropane, and the bromide here breaks off. Okay, and it forms something like this with a plus. This is called a carbocation. You don't know the detail. You don't need to know the details of this, but basically what we want to know is that it can have multiple steps. And then water plays a role in the second step. So water reacts with this carbocation to form this cation, and then that cation gives off a proton, acts as an acid to give us our product. Okay, so there's a lot more going on than we knew about. The other important part of this is that each one of these steps has its own rate law. Okay? And the overall rate, or what influences the overall rate, is going to depend upon the relative rates of these individual steps. Okay? So, in this case, the first step is a very slow step. So this one has a higher E sub A, higher activation energy. The second step is fast. And the third step is fast. Okay, so it turns out when we look at kinetics of these reaction processes, it's going to be the slow step which influences the overall rate. Okay, so the overall rate depends upon the relative rates of what we call elementary steps. So we can break that balanced one into individual steps, but each of those 1, 2, and 3 are broken down as far as they can go. Okay? So when we have an elementary step, we can write the rate law directly from the stoichiometry. Okay? So the rate of the first step we can see is bromopropane, and there's only one of those over there, so it's first order. The second step, both of those are first order here, likewise on the last one. Okay? So, we'll get back to that. Okay, so here's my analogy. So that we have a slow step, and the slowest step, we call it the rate determining step. All right? So my analogy is this, is me pouring this blue liquid through a couple of different funnels. All right? So let's say we have 3 types of funnels, various, the hole is various sizes. All right? So let's compare some of these. Or let's just look at the 3 possibilities. So we pour into a big one first, and then it goes through a small one to a big one, a bigger one to a small one, or 2 big ones over here. All right, so what do you think out of all of these, if it's dripping out of the bottom, which one would be fastest? D? Everybody agree? Yeah, so D would be the fastest, right? So this is basically saying that we have 2 fast steps. All right? Let's compare, though. Let's compare A and C. All right, so what we have the same bottom step, and the top 2, we have the intermediate funnel on the left, we have the biggest funnel on the right. So which one of those is going to go faster? C? So what happens if we pour that in faster and faster? What's going to happen? Is it going to speed the rate up at the bottom? No, it's going to likely, unless it flows over the top into the bucket that we want, right? If it has another route. But the point is that even if we pour it into the funnel faster, it doesn't force it out faster out of the bottom, right? So, in fact, A and C would give us a rate coming out of the bottom that's the same. All right, so these 2 would be the same rate. what about if we compare A and B? Which one of those would be faster? They'd be the same as well, right? Because in each one of these cases, they have a thin funnel. So that's going to be the rate determining step, right? And the overall rate cannot go any faster than that rate determining step. Okay? So the reaction cannot go faster than the rate determining step. Okay? So let's go back to the reaction. Compare. So we saw that in here, did I do those? Yeah, that this one is the slow step, and then these two are fast. Okay? And here's a more complicated reaction coordinate diagram, which may go for this reaction. Okay? So what we see is we have 3 different peaks here, right? Each one of these is called, what did we call the top of the peak? So what? The transition state, right? Transition state. And there's actually 3 of them. So this tells us that we have 3 different steps. Okay, step 1 is going from our reactant to this kind of higher energy product there. So if we have a product that's in the middle of these reactions, anybody know what those are called? We got 2 of those. These are called intermediates. Okay, so step 1 goes from our reactant to an intermediate. Okay, goes from down here, goes up over this transition state to this intermediate. Step 2 goes from this intermediate, is acting now as a new reactant, over the transition state to another intermediate. This goes over another transition state to the final product. Okay? So, what do we see here? We've talked about how step 1 was the slowest step. Can we understand why step 1 is the slowest step if we look at that reaction coordinate diagram? Yeah, why would it be the slowest? Right, it has the highest activation barrier, right? Or we can put it too, is it the rate determining step is the one with the highest energy transition state. Okay, so no matter how fast we make the second and third steps, it's not going to go any faster because the first step is the rate determining step. Okay, so in this scenario, when the first step is the slow step, we can figure out, we can take the rate law of that first step, and that will be the rate law for the entire reaction. Okay, so this is going to be the rate law for the overall reaction. Okay, so we have the first step is slow, and so this becomes the rate law for the whole reaction. Okay, so in the scenario where we have multiple steps and the first step is the slowest. Okay? We can take that rate law directly from the stoichiometry. All right, if we have a situation where the second step or a subsequent step is the slow step. So if we look at these 2 steps, here's our balanced equation. And we see we have 2 steps, and here's the slow step. The rate determining step is the second step. Okay? So we can say that, that the rate will be the rate law for that second step. However, we're going to see we want to modify it some. So the rate is therefore going to equal the rate law for this second step. So NOBR2 NO, oh, I didn't put my K in here, K equals this. Okay, so if we look at these two reactions, what we're trying to do is really go from, these two species to this product. All right? And what role is this NOBR2 playing in this reaction? Does it show up in the balanced equation at the top? No, it doesn't show up there, right? So what role is it playing? What is it? An intermediate, exactly right. So it gets formed in the first step, then it reacts and forms a product, okay? So this is an intermediate. Okay? And we'd like to make our final rate law in terms of reactants and not in terms of intermediates. Okay? So we basically don't want an intermediate in our rate law. Okay, so we're going to have to do some manipulating. Okay, so what we're going to do is we're going to look at that first step. And this is still kind of a specific situation, all right? There's a ton of other situations that we're not going to go into, right? There might be all kinds of complicated things. But this first step is fast, and we have arrows going both ways, so it's reversible. Okay, it means it's going back and forth. All right? And so this is what we could call an equilibrium. Okay, and we're going to spend a lot of time talking about equilibrium in the next few chapters. Okay, the thing that's true when we have an equilibrium is that the rate going forward is going to equal the rate going back. Okay? And remember, the rate is the concentration times the rate constant. Okay, so we'll say that the rate going forward, so that would be K1 times NO times BR2. Okay, so this is forward. It's going to equal the reverse rate. So this has a K minus 1, so that's the rate constant going back, times NO BR2. All right? So what we're going to do in order to put our final rate law to take it out of terms of the intermediate is we're going to solve this equation for the intermediate. Okay, so here, so we're going to solve, for the intermediate. Okay, so what do we have to do? So here's our intermediate right here, right? So we want to get that all by itself. Okay, so what do we do to get that all by itself? Divide both sides by K minus 1, right? So then we're going to end up with K1 over K minus 1 times NO times BR2, and this equals the concentration of the intermediate. Okay, so you're wondering, why are we going through all this? This is really dumb. But what we're going to do now is we're going to take this value here and we're going to substitute it in here. Okay, so they're equivalent, right? So we're going to rewrite this rate law. We're going to go rate equals K. K, is that how I want that? K, no, that should have been K2. So K2, and we're going to substitute that in, so we're going to have K1 over K minus 1 times NO times BR2, all right, and times NO. Okay, is everybody following where I'm getting all of this stuff? Okay, so what I did is I took, so this is equal to NOBR2. So this whole thing right here is equal to NOBR2. So I took this whole part and I stuck it right in here. I substituted it in, okay? And so then we get this, and what we see is that we've got two NOs here, so that's our NO squared up here. So if we simplify it, we get this thing here. So we get two NOs, so it's NO squared times BR, which is here. And what they've done is that they've taken this whole thing, this K2 times K1 over K minus 1, and they've just said, oh, we're going to generalize that. We're just going to call that whole thing K. All right? So then, at this point, they have everything relative to, the reactants. So we can measure the changes, the initial rates, and we can calculate those things out. The harder thing, though, I think later is if you want to then separate these different rate constants from one another. It's more challenging to do. Yeah?
How did it go from NO to NO2?
Okay, so the question was, how did it go from NO to NO2? So up here it's a 2, right? And it's because we have NO and we have NO. So we have...
Not raised to the 2, just the O2. Because it's NO in the bottom equation, and then in the top equation it's NO2 raised to the 2.
Oh, NO2. Okay, probably because I made some mistake here. Let's see here. NO2... I think it looks like that this 2 shouldn't even be there, right? Because there are no NO2s in the whole thing. So that's just a typo that I made. Thanks for pointing that out. Yeah, so now we have two NOs, makes it squared, BR2, and then they're just lumping all those Ks together. Okay? You guys look just about as bored as you could possibly be. I know, not all of the thrilling. All right, so let's finish off this chapter. So that's the part about the mechanism. So the important thing is that a net reaction or a balanced reaction may be made up by a series of elementary steps. Okay? If we have an elementary step, we can write out the rate law directly from its stoichiometry. Okay? And then the other important thing is that the rate is going to be determined by the slow step, the rate determining step. If that first step is the slow one, then that's the easy situation. We can write the rate law for the overall reaction just directly from the rate law for that elementary step. If a subsequent step or the second step is the slow step, then we kind of have to do this other algebra manipulation, this substitution, in order to get our rate law in terms of the reactants and not in terms of the intermediate. Okay? All right, so the last thing we're going to do on just a couple of slides is we're going to talk about catalysis, so the presence of a catalyst. So that was one other way that we talked about early on that we can influence the rate of a reaction. Okay, so a catalyst in general is some substance that can change the rate of the chemical reaction without being consumed. So if it's drawn into steps, usually we see it being used and then it gets regenerated. So it'll be a reactant and a product, and it just kind of recycles itself around. Okay? Catalysts can be either homogeneous, which means that they are in the same phase as what the reaction is taking place in. So same phase as the reaction. So for example, if we were doing a reaction just in aqueous, in water, sometimes we can use just an acid. So H plus is the catalyst. So that H plus would just be dissolved in the solution. Okay? A heterogeneous catalysis is one where the catalyst is in a different phase. So it may be that the catalyst is a solid and the reaction's in the liquid phase, or the reaction is in the gas phase and the catalyst is a solid, things like that. So it's in a different phase than the reaction. Okay? So the way that this usually works is that the catalyst somehow functions by reducing the activation energy. Okay? So if we started out with something like this, right? So let's say we're just going from A to B, and here's our activation energy. Okay, so one way that this could work is that it just is able to lower that barrier. So we add our catalyst, and we look at our graph, and the E sub A is much smaller. Okay? It doesn't change the relative energies of the reactants and products. Okay? It just affects the activation barrier. Okay? The other way that it can work is that sometimes it changes the actual mechanism of the reaction. So it reacts with a reactant to form maybe a different intermediate. So we could also have something like this, where it goes from here. Oops, I don't want that very big. And it maybe has another hump in here, okay? Or it changes the mechanism, okay? So we see that there's another intermediate, so we know the mechanism is different. But still, it's not changing the relative heights of the reactants and products, all right? Examples. Seems like I said already. One example of a homogeneous catalyst might be an enzyme catalyst. So in our bodies or all living systems, reactions are catalyzed by enzymes, by proteins, all right? And really this is critical to living systems because there's all kinds of reactions that take place in our bodies that if they just took place just any old time, then we'd essentially fall apart. So for example, I don't have much time here. So one reaction could be, I'll get to this other one in a minute, so I'm going to draw it out like this. We haven't really looked at these kind of structures, but this is a chain. So this could be a representation. These long zigzags are just long carbon chains. And this would be what we call a triglyceride. Anybody know what a triglyceride is? What is that? It's a fat, right? And so there's a reaction that we could react this with water. It's called a hydrolysis. And what it does is it cleaves all of these bonds. These are called ester bonds. So it cleaves this one, and this one. Okay? And gives these things called fatty acids. I'm not going to worry about exactly how long these are. Plus this molecule with 3 alcohols on it is called glycerol. All right? So essentially the fats are falling apart. If that reaction took place just randomly, then all of our fats would just melt away. So that would be terrible, right? But in fact, our bodies would like fall apart. All right? So in reality, this reaction is very slow to take place just chemically. But there's an enzyme that can cause it to happen at a reasonable rate. So your body can control exactly when that's going to take place and when it's not going to take place. Another example up here is in this reaction of putting, so this is my cartoon of a protein. It has an alcohol on it, and it can react with phosphate, okay, and generates this thing called a phosphorylated protein. An enzyme called a kinase puts it on, and another enzyme called a phosphatase takes it back off. And this phosphorylation process is oftentimes like a trigger or a light switch for an enzyme. So it can go either way, but oftentimes when you phosphorylate it, it can then become activated and it carries out its duties, hydrolyzes the fat or something. And then when the body doesn't want it to happen, then it dephosphorylates it. And so it turns it on and off as needed. All right, so that's super critical for living systems. Dr. Henge upstairs works on these phosphatase enzymes. So they look at just what controls it. Here, and you don't have to take much here. This is called a hydrogenation reaction. So this is a kind of reaction where we add hydrogen to a double bond, and it makes a single bond. So this is how unsaturated fats can be hydrogenated to make saturated fats. And in this case, usually it's done as a heterogeneous. So we have some metal. Usually this is like platinum or palladium. And the hydrogen and the double bond can stick down onto the surface, and the reaction takes place, and then they're released. But we have this metal that doesn't dissolve in the solution, and so in the end you just get rid of it by filtering it off. Okay? Or there's times where you can have a solid catalyst and you just blow a gas across it, and the reaction takes place as it blows through. So those are examples of heterogeneous catalysis. All right? So I'll see you guys on Wednesday, and we'll be starting into chapter 15 on equilibrium.